Well, thanks for coming out tonight. As you can tell, we're all pretty excited about MAVEN arriving at the planet, and we have a nervous about an hour and a half that many people are chomping on their fingernails at Lockheed Martin. But I have a little bit of time to tell you about what we're planning, and at the very end I'll give you a lowdown on where we're at in the timeline. Let me set the context here. Nilton has described beautifully the Phoenix and InSight and the lander missions. I'll show you here a bit about where we're at in terms of the overall flow for the Mars exploration program. In this first box here are operational spacecraft, Odyssey and Mars Reconnaissance Orbiter. These are orbiters from the US. Mars Express is a collaboration. This is an orbiter that the Europeans have had operational for over 10 years now, and we've had a lot of cooperation with them. Opportunity and Spirit and Opportunity. Opportunity is still working. Phoenix is completed, and as you heard, MSL is still in operation. We launched MAVEN in November of last year, the 18th, and I'll come back to that. It's arriving today. InSight will launch in early 2016 and arrive later the same year. The Europeans will launch a trace gas orbiter, and we have collaborations with them with an Electra, a communications relay package. The Europeans will also land something called ExoMars. Maybe this is the launch in 2018. And we have an instrument on board, MoMA. And finally, there are plans in 2020 for another rover similar to MSL, presumably a vastly different location. You may know about what they're planning there, but it should be a much different location, I would imagine. So, motivation for MAVEN. We've had a theme over the last decade or more of following the water. And by that I mean we're following the sources of water and its location to determine if life ever arose on the planet, to characterize the climate of Mars, to characterize the geology of Mars, and to prepare for human exploration in the future. This is a list of all the spacecraft previously, many of them I've just talked about, and each of those has been primarily focused upon the water that might be at the surface or under the surface, as we've just heard about. And MAVEN has the opportunity to look at the big picture from the top down. MAVEN will approach look at the top of the atmosphere and assess the possibility that water and carbon dioxide may have been lost from the very top of the atmosphere, stripped away. So this is a little bit different approach. Where did Mars' atmosphere go? Atmosphere today is cold and very dry, as we've just heard. This water and CO2 could either go into the crust or it could be lost to space. So this focus of MAVEN is this volatile loss to space, a stripping away of the top of the atmosphere, if you will. This is another likely mechanism that the planet may have been able to lose its water. It's believed that Mars had an intrinsic magnetic field like the Earth does in the past, and for some reason it turned off quite a long time ago, and that left Mars exposed, if you will, to the solar wind, the particles and the magnetic fields emanating radially away from the sun, and that left Mars exposed, its upper atmosphere exposed to the solar wind where it could be stripped away. We've seen evidence in Nilton's pictures before of a possibility of water flowing on the surface, and even some of the rocks in fact show that there was the hydrodynamic and hydrothermal effects. There's also evidence that volatiles are being lost to space in this right-hand panel here. This is color-coded. The sun is to the right. This is Mars right here. And these color-coded pixels indicate ions, escaping ions that are leaving Mars at the present time. So this is evidence that the upper atmosphere is really being lost from Mars, blowing downwind from the planet. So this loss to space may play a very important role in describing the history of water over Mars' history and where the water has gone. And so MAVEN will actually explore that in a very self-consistent way for the first time. The science goals for MAVEN are outlined here. What's the current state of the upper atmosphere, the top side of the atmosphere, and what processes control it? What's the escape rate of that atmosphere at the present time? And how does the sun, among other things, control that loss? And what's the integrated loss to space through time? This last bullet I'll come back to. It's not something that can be addressed directly, but indirectly with numerical models. And I will come back to that. The ultimate question, and we've heard a bit about that already, that Mars probably was a very habitable place for life to have erupted in the past. But the question still remains, where did the water go? Okay, a little bit about the mission. We had a 20-day launch period. It opened on November 18th. We launched precisely at the very first moment in that launch window that we could have launched at about 1:30 Monday on November 18th. I was there, and there was not a dry eye in the audience, among the scientists at least, and my family can attest to that we're there. Many people had waited for this mission for a long time, and to see it launch was just amazing. It launched on a Atlas V, a very capable launch vehicle. Once it was injected into its trajectory toward Mars, the engines were turned off, and Newton was in the driver's seat, basically, for the next 10 months, where Newton's been working very well on a ballistic cruise to Mars. You can see here's the Earth at launch, and this very, very strange pathway to Mars. Remember, the Earth is revolving around the sun, and so is Mars, and so you launch toward where Mars will be in 10 months. This is a very curious thing that you have to do, but orbital mechanics works this way, and that's precisely what's happened. Orbit insertion, this is in UTC. This will be tomorrow morning in England, for instance, but it's this evening here. The capture orbit will be about 35 hours. The 380-kilometer periapsis, I think it's about a 44,000 kilometer apoapsis when we first arrived. And that orbit will eventually shrink. It will be manipulated to shrink to a 4.5-hour orbit, and periapsis about 150 kilometers, apoapsis about 6,200 kilometers. This is the mission complement. There are 8 instruments altogether. Briefly, there's a mass spectrometer that looks at the neutral gas and the ions. So as the spacecraft dips through the atmosphere and comes out, this instrument will operate below about 500 kilometers. It's called NGIMS. There's a remote sensing package, the imaging ultraviolet spectrograph or spectrometer from Colorado. This looks at the atmosphere either tangentially or nadir down on the planet and looks at the emissions from the atmosphere and is able to unfold the neutral densities and temperatures from that. Here's several fields and particles instruments. This measures the solar wind particles and the magnetic fields. There's a magnetometer from NASA Goddard. Langmuir probe from Colorado. This measures electron temperatures and densities. SWEA and SWIA, this is solar wind electrons and solar wind ion analyzers, the superthermals, very hot ions and electrons. And top here is static. This is superthermal and thermal ion composition. So this is a combination of both very hot and cold ions. And the SEP is a solar energetic particle instrument measuring the very energetic particles that come from the sun. So you have a suite that looks at the solar output, a suite that looks at the neutral and ion atmosphere, and a suite that looks tangentially and remotely at the atmosphere from a broad perspective. This shows the spacecraft. This is kind of a cartoon of the spacecraft. It's a monoprop propulsion system. The weight fully loaded with its fuel, nearly 2,550 kilograms. Dry mass is nearly 900, so you can see that most of the mass of the spacecraft is the fuel, and a large fraction of that is going to be used in a little less than an hour as they make the burn to get into orbit.
For how long?
33 minutes.
Oh.
So it's quite a long burn. And they have to slow it down significantly to make that happen. This shows this is the booms for the Langmuir probe. I think these are several meters. I don't remember exactly how long. This is the solar panels from tip to tip. This is the magnetometers are on the very end to avoid contamination from the spacecraft, the rest of the spacecraft. This is an articulated arm that moves and is able to orient and look in the atmosphere and point the IUVS static and the NGIMS instruments, either into the RAM or looking tangentially through the atmosphere for a limb profile. Okay. This shows the size. The size of the spacecraft is about the length of a school bus, just to give you a perspective. So this is not trivial. It's about the weight of a GMC Yukon. Okay, so this gives you, again, a little bit perspective. This is not a small spacecraft. Okay, this is a bit of a cartoon, what regions of the atmosphere we'll be exploring from an orbit. So this is a cartoon that shows the closest approach, about 150 kilometers typically, out to about 6,200 kilometers at apoapsis, periapsis, apoapsis. And you can see the different instruments listed around different parts of the orbit while they'll be operating and taking their ideal measurements. You can also see that at different parts of the orbit, there's no part of this orbit that's not involved in some kind of data taking. So there's a big scheduling process that goes on to help the folks decide who gets turned on when and for how long. So you can optimize the measurements that each one will make, and everybody gets a little bit of what they want, but maybe not everything that they want. So this goes on all the time, trying to decide the duty cycle of these instruments so that everybody gets something that they want, but not necessarily everything. I'll be involved in the deep dipped orbits. These are 1-week campaigns, 5 times during the mission, in which we'll dip down a little bit lower than 150 kilometers. We'll go down to about 120 kilometers or lower. And the upper atmosphere is divided into a part of the atmosphere below about 120 kilometers that's well mixed, called the homosphere. Above that is the heterosphere, where species begin to separate from one another and diffusion takes place. And that level is called the homopause right here. So it's very important in some of our analyses, particularly for isotopic abundances, to be able to go below the homopause. And this was specifically put in for that very opportunity to take place. These take place for about 1 week each and go down significantly lower. These have to be managed very carefully because you're now in the part of the atmosphere that has drag on the spacecraft. And so we have communication that's very frequent. Instead of twice weekly communication with the spacecraft, it's absolutely every day. And we have deep space network tracking every single day and throughout that day to make these deep dips possible. So this is not trivial to schedule this, but it's very important for the science that we'll be doing. The sun has a solar cycle. It's about 11 years, typically for our purposes here. So this graph shows sunspots, number of sunspots from this current solar cycle that we're in, up to 200. And this is year at the bottom. So the MAVEN primary mission, which is about 1 Earth year, is shown right here. This shows the oscillation of the solar cycle. High points where there are a lot of solar sunspots and low points where there are very few. And we'll arrive when the sun is at moderate activity. And so we'll be able to look at the output of the sun, its impact on the upper atmosphere, and its ability to strip away the constituents at the top of the atmosphere during this time period right here. Okay, I thought you'd find this instructive. This shows where the key players are. Partner institutions throughout the United States. LASP, Laboratory for Atmospheric and Space Physics, is in Boulder at the University of Colorado. This is where the principal investigator, Bruce Jakosky, lives. This is where the Science Operations Center is located, so the data comes down. Once it's relayed through the Deep Space Network, it comes down to Boulder. It's processed initially, and it's sent out to all the participating scientists, all the scientists on the team. Lockheed Martin is the bus provider and the integrator and our strong partner, as we've just talked about before. Berkeley, the Space Sciences Laboratory at Berkeley, has many of the particles and fields instruments, not all of them, but many of them. Very key player, and JPL provides the Deep Space Network as indicated here. There are many other institutions that are participating, but these are the primary partners. This shows the entire science team, all the instruments that I pointed out before, and the red folks here are the team leaders. Bruce Tchaikovsky is our PI. Deputy PI is Janet Lumen from Berkeley. And Joe Grabowski is the project scientist from Goddard Space Flight Center. Here at Michigan, we have, this is an interdisciplinary scientist, IDSs, myself and Andy Nagy, my thesis advisor from years past. We're both IDSs. I have to stop and say something about this. Andy Nagy, as well as many others, including Jim and my former mentor at the University of Arizona, Don Hunton, were instrumental in this mission first being thought of almost 30 years ago in a special report made to NASA. And we are flying almost that entire suite of payload instruments, as I recall, almost to the T. So 30 years later, there was a participating scientist call given by NASA headquarters, and these were the selected individuals to come on board right about the time of launch and participate and bring new ideas to the science that we'll be able to do. And Mike Comby here in our department was another fellow brought on board. So these are the Michigan folks listed in purple right here. A little bit of history about the mission. 10-month cruise, initial checkout of instruments was completed. Subsystems were operating initially in the cruise. There were 2 trajectory correction maneuvers carried out, TCM-1 and 2. TCM-3 was canceled, and I heard that TCM-4 was canceled as well about a week ago. And we may or may not have had 1 or 2 trajectory correction maneuvers earlier today. I have not heard yet, but things were very much right down the corridor of what they expected. And this is a listing of the early phases of early selection all the way down to the present. So you can see this timeline. This is a long time to bring about a mission from concept, initial selection, down selection until you're finally selected to actually run your mission, different phases that you have to go through, lots and lots of reviews until you finally launch, and then the science begins. This is not a short-term endeavor. This typically will span more than a couple doctoral students in your program. So this shows I'll show you some pictures now. The proposal, site visit, and presentation at NASA headquarters. These are all steps you have to go through. This fellow right here is Bruce Tchaikovsky at Colorado. This is Dave Mitchell at Goddard. He's the program manager. Bob Lynn was once the deputy PI and has since passed away and has been replaced by Janet Lumen and other folks that I'll move on from right here. Countless reviews. The acronym, the saying that I heard was that reviews are only held on days that end in day. And so they were always held, countless reviews over many years. And so these folks are sitting here and doing their job quite well. This shows the spacecraft in assembly. Okay. Let's see. It is moving. So here's it's undergoing final testing. The solar panels are coming out here to their fullest extent. They're finding if everything is moving and working right. This is the high gain antenna, I believe. It's being rotated. This is in the high bay at Lockheed. Okay, I think that's it. It starts its journey to Mars by first moving from Lockheed to Kennedy Space Center. So this shows the different phases. It gets boxed up and put on a crate, loaded onto a transport plane of some kind, a shuttle landing at the Kennedy here. A shuttle landing strip is used at Kennedy here with this transport plane, and then the container finally arrives. Once it gets there, you have to get it ready for launch. This is called ATLO, putting everything together. They button it up. This is the fairing right here that it fits inside of. It gets moved to the launch site where it gets mated to the rockets. It's important to do this very carefully. Okay. So this is rather tall. I don't remember the dimensions precisely. But this is a building built specific for this purpose to launch Atlas V rockets. This shows the team during launch week of mid-November. This is a group picture the night before, right in front of the launch site. I think we're a football field away or so here, and the entire team. This is the ops team at Lockheed Martin, illustrated here. The JPL team, DSOC, and the NAV team at JPL as well. This is the launch itself. The mantra was go Atlas, go Centaur, go MAVEN. So these are the different launch stages, and then the final spacecraft itself sitting on the top. This was taken very close to the launch site, as you might imagine. The actual viewing is from several kilometers away, and even at that distance it was stunning, absolutely stunning. We've been busy here at Michigan on the science end, preparing for the data that we hope to be returned here very shortly. This is the cartoon that I'm not going through all the details, but what I want to point you out to you is the sun is the driver here, providing the energy inputs that we need. We have a lower atmosphere here from the ground to about 100 kilometers, an upper atmosphere or a thermosphere of about 100 to 200 kilometers, and then an atmosphere, a very extended and hot atmosphere above that called the exosphere. Inside of the thermosphere is an ionosphere is embedded. This is the neutrals get ionized in one way or another, and they're coupled together very nicely. And because Mars does not have much of an intrinsic magnetic field, this solar wind, the particles and fields that exit and move downwind of the sun actually have access to the thermosphere, ionosphere, and exosphere, and they sweep away the upper atmosphere as it goes by. And this is what we're measuring. The loss rate of the neutrals and the loss rate of the ions. And as you lose hydrogen and oxygen, you'll eventually lose water. And as you measure that in the current time and get those loss rates, both neutrals and ions, you can integrate that loss over time, estimate what its loss might be over time, and figure out what might be the volume and depth of water covering the whole surface of Mars that might have been lost over its history. We can't actually go back in time to what might have been the case for early Mars, but we can look at other stars like our own, G-type stars, and see their output at different stages of their development. Use that as inputs to our models that we've tuned to match the observations in the present day and integrate backwards in time. So that's the strategy that we're using. It's not perfect. It would be nice to have an observation early on, but G-type stars in early phases of their history is the best that we can do. So you see these different atmospheric layers and how they're connected to one another. So if you're going to measure and understand the loss rates from these different processes, you actually also need to link the models to one another. And that's what we do here at Michigan, is numerical simulations. So here's the thermosphere ionosphere model, an exosphere model, and Uni, where is Uni? She runs the exosphere model here with her boss, Mike Comby. An MHD model, my student Xuan Fei is in the back. He runs this model right here. And these models are beginning to talk to one another. So as you supply the output from one and use it as input to the other, you're connecting the physics of these different models, and you're able to look at the loss processes from the models in concert with all the physics of all these different regions. And this has not been done before, and we'll have data to compare to hopefully very soon. Cruise details. So this is where the Earth and Mars were at launch. I showed you this trajectory, which was quite odd, but was needed in order to actually arrive at the planet on time. We haven't been completely idle as we've been approaching Mars. There have been a lot of checkouts of the instruments to make sure they're working properly. We've also been able to get some of them to return data. This is the first data from the ultraviolet imaging spectrograph on May 21st, about 4 months out from orbit insertion. Even though we were a great distance and Mars was only a pixel, just a small pixel, you were able to get some kind of a spectrum, and this was really a reflected spectrum of the sun. So this is the ultraviolet sequence right here, and it shows that we were able to get a spectrum that resembled the sun. The instrument is working, and as we get closer, it will sample the atmosphere. Another suite of instruments is the particles in field. I just have time to talk about one, the solar energetic particle instrument. We measured fluxes from MAVEN. So here's a cartoon. This is one axis. These are two axes. This is the sun and the spiral arms of the magnetic field from the sun. This is measurements from near Earth on these different dates. March, April, May, and June right here. The particle fluxes is indicated by the different colors. And this are similar days, March, April, May, and June at MAVEN. You can see that this MAVEN trajectory is approaching Mars here, and you're seeing these energetic particle fluxes at Mars similar to those at Earth. So what we're doing is we have a monitor of the solar wind beyond the Earth, a space weather monitor, if you will. And this is exactly what we need at Mars in order to be able to do the science that I've just described to you. We have a bizarre twist in this mission. I call this science that comes by accident. And some of the best science is done by accident. And we have a comet. It was discovered in 2013 in Siding Spring Observatory. And this is a comet that will intersect very closely with Mars on October 19th. We'll be in orbit just about a month. They rearranged the checkout procedures so that we can actually image and sample the atmosphere and image the coma of the comet. This is a rare occurrence that a comet should get that close to Mars, and even rarer that we should be there at the same time. This is a long period comet on its first passage from the Oort cloud, the outer solar system. It passes within 132,000 kilometers from Mars. This is about half the distance from here to the moon. It's quite close, okay? Now, this made people very worried at first that we were going to have problems on the mission, so they did detailed studies about the dust output from the comet and discovered that it probably would not be a problem. However, they asked us to make sure that we did not open most of the apertures to our sensitive instruments at closest approach to the comet. And so we'll be taking data a couple days before closest approach, stopping at close approach, and then a couple days afterwards, okay? So the plan is to look at the comet coma and image that and take spectra of that, look at the atmosphere so you have some reference of what the atmosphere of Mars is doing before comet encounter, go through the encounter, and then do the same kind of sampling again 2 days afterwards. And you might expect the dust that traveling at, isn't on here, at 56 kilometers per second. You might expect the dust to heat the atmosphere of Mars. And so there are instruments on board that can give us some insight as to whether that's happened or not. And comets are notoriously for having water output. And so if those molecules make their way to Mars, it might actually change the chemistry in the upper atmosphere as well. And so they'll be looking for hydrogen in the upper atmosphere and water-based ions and other molecules. So this is free science, if you will, and it was a laborious couple months while the project went through the effort of redesigning their scheduling and turning on instruments early so that this could happen, and we're really glad that they did. This shows this comet at very inclined orbit, and the encounter is in about a month. MOI, so this plot was put together on the 4th of September, and that was here, and now we're right here. And we're traveling at, before the burn, we were traveling at about 2 miles per second or 3 kilometers a second, moving along quite nicely. And so this is the last plot that I have, a table that I have. It shows the timeline of the encounter today in the last 24 hours. This shows MOI time and the date and time in Eastern. And I need to remind you that there's a delay time. So this is event time on the Earth, okay? And this will be important here in a minute. These are burn times right here. They pressurized if they needed the burns for trajectory correction. They pressurized the tanks about an hour out, reconfigured the low gain antenna because that will actually be doing the work that we need to do. The high gain antenna will be pointed the wrong direction. You slew to start the burn, so you have to actually move the spacecraft all the way around, so that the burning rockets are in the direction of the spacecraft motion. So it actually slows the spacecraft down. So it has to have an attitude slew and a change in attitude. The 6 main engines are turned on in a staggered fashion, and they burn for 33 minutes. You slew back to Earth point. At the end of the slew is here, about 55 minutes afterwards. Transition for the high gain antenna. You confirm the burn, and the orbit navigation confirmed a little bit later. We are going to get a confirmation just about at 10:30, I've been told, of a preliminary indication whether the burn was successful. It'll be a few hours more before we know that the orbit, it was achieved exactly as anticipated. But this is event time as received here on Earth. This is actually going to start, this burn is actually going to start at 9:37, and we won't know about it for 13 minutes. So this is event time as listed here on the Earth. It's about 12 to 13 minutes transit time for radio communication right now. So let me stop, because I think we're going to have NASA feed pretty soon, but let me entertain a few questions. Mars is a very dry and cold place today, and it may have supported a lot of water in the past. The question is, where did the water go?